All right, let's go on to chapter 3. It talks about determinants and diagonalization of matrices. In particular, we'll talk about eigenvalues and eigenvectors. But first, we'll start with determinants. A determinant is a number related to a square matrix that indicates if the matrix is invertible. If the determinant is 0, then the matrix is not invertible. If it's non-zero, it is invertible. They also have application in actually computing an inverse, so we'll look at that method for computing an inverse actually next time. And then they're also related to the eigenvalue problem. So we'll first look at a particular method for finding determinants called the cofactor expansion method. Cofactor expansion. And if you recall, we defined previously the determinant of a 2 by 2 matrix. So let's take matrix A with elements A, B, C, and D. And then for the determinant, we'll use this notation, the determinant of A. Okay. Or we'll show the matrix elements surrounded by absolute value bars, A, B, C, D. So this is the other notation that's used to represent the determinant of a particular matrix. Now for a 2 by 2 matrix, we saw that it was invertible as long as, and this is how we define the determinant, it's, let me try and rewrite that again, that's A times D minus C times B. An easy way to remember that, it's the product of the terms along the main diagonal minus the product of the terms along the off diagonal. And that applies again for a 2 by 2 matrix. Again, A is invertible only if the determinant is not equal to 0. Now for a 3 by 3 matrix, A, which will indicate with these elements, A, B, C, D, E, F, G, H, I, you can show that this matrix is only invertible if the determinant is not equal to 0, where the determinant of A, in this case, is this number. And he has this proof in the book. But it's A times the determinant of the 2 by 2 matrix that remains when we eliminate the column, the row in the column that contains A. So it's times this 2 by 2 determinant E, F, H, I, and then minus B, I'm working along the first row here, and I'm taking this method because it's related to the cofactor expansion method that I'll talk about in just a second, minus B times the determinant of the 2 by 2 matrix that remains when I eliminate the row and column containing B. So that would be the determinant of D, F, G, I. And then finally plus C times again the determinant of the smaller matrix that remains when I eliminate the row and column containing C. So that leaves D, E, G, H. And you probably remember perhaps from high school a shortcut method for determining the matrix, for determining the determinant of a 3 by 3 matrix. And I'll talk about that in just a second. But I want to talk about this matrix or this method because it actually leads to a method that applies to an arbitrary size matrix, and it's called the cofactor expansion. So we have, a special case formula for the 2 by 2, and we'll look at a special case method for a 3 by 3. But in general, we can use this cofactor expansion method for an n by n matrix A with elements A, I, J, the determinant of A is equal to, I'm going to write it going across using the elements in the first row, the first element times what's called the cofactor, the C11 cofactor of A, cofactor corresponding to this element, plus the next element in the first row times its corresponding cofactor, plus go entirely across the first row. The final term in the sum is A1n, the last term in the first row, times the corresponding cofactor of that term. Okay, where these cofactors are equal to, I'll write that down, cofactor Cij of A is Cij of A is -1 to the I plus j factor. So this term will always be either -1 if this is odd, or it will be +1 if I plus j is an even number, times the determinant of Aij. Aij is a smaller matrix than A. If A is n by n, Aij will be n-1 by n-1. So let me put down the definition of the smaller matrix. Aij is the n-1 by n-1 matrix obtained by deleting row I and column J from A. Okay, so this particular cofactor expansion method for calculating a determinant relies on being able to find the determinants of smaller matrices. So it can be applied recursively to write the determinant of a 5 by 5 in terms of a sum of determinants of 4 by 4 matrices, and then each of those determinants can be written in terms of the determinants of 3 by 3 matrices, and then correspondingly those can be written in terms of the determinant of 2 by 2 matrices. So let's look at a particular example. Let's take the case where A is equal to 2 minus 4, 1, 3, 0, 5, 7, 6, 0. Okay, and then the corresponding determinant of A, using the definition of the cofactor and using the elements in the first row, it's going to be plus 2 times the corresponding cofactor. So 2 times, we eliminate the row and column containing 2, and then we want to find the determinant of this case, the smaller matrix, the 2 by 2 matrix, and then minus 3, the minus here because of the alternating sign of the plus minus, eliminate the row and column containing 3, and I'll have minus 4, 6, 1, 0, and then finally plus 7, eliminating that row, that column, I'll have minus 4, 0, 1, 5. Then now I've got it written in terms of the determinants of these 2 by 2 matrices. So this determinant is 0, minus 30, minus 5 times 6, and then the next term is minus 3. Then here I'll have minus 4 times 0, which is 0, minus 1 times 6, which is minus 6. And finally I'll have 7. I have minus 4 times 5, which is minus 20, minus 1 times 0. So this becomes minus 60 plus 18 minus 140. So that's minus 240 plus 18. The determinant in this case is minus 182. Okay. Let me just give you a mnemonic device for determining the signs in the cofactor expansion. Okay, so the first element is going to be associated with a plus sign. The next element in the first row would minus, and then the signs alternate. Okay, and then in the first element in the first row would be a minus sign. Second element, again, the signs would alternate. So they just alternate as we go along any row and column in this manner. Okay. Okay. And furthermore, although I wrote the definition of the cofactor expansion using the elements in the first row, the cofactor expansion can actually be done along any row or column. So you can take advantage of that by looking for rows and columns that have a lot of zeros in them. Okay, so let's do a 4x4 example. 3, 5, 2, 6, 0, 1, 6, 3, 0, 2, 0, 1, 0, 0, minus 1, 0. Okay, and I see here the first row has only a single non-zero element. Alternatively, the last column actually has a single non-zero element. So I could do the cofactor expansion along either the first row or this last column, but let's just do it along the first row. You might want to show that you get the same result by using the last column. Here, plus minus would be the sign assignment. So it's going to be 3 times the corresponding. Now I'm starting with a 4x4 matrix, so when I eliminate that row and that column, I'll be left with the determinant of a 3x3 matrix. 1, 2, 0, 6, 0, minus 1, 3, 1, 0. And then all the other terms are 0 in this first row. So I have plus 0 times the corresponding determinant plus 0 times the corresponding determinant. So that cofactor expansion just reduces to this single term. So again, I can greatly reduce the amount of work by looking for any row or column that has a lot of zeros. I need to find the determinant of this 3x3 matrix. Well, let's do that along this third column because I only have a non-zero term there. And then so the assignment would be plus minus plus minus here. So I'm going to have minus 1 for the sign, and then I have another minus 1 times the term. Okay, and then the corresponding 2x2 matrix that's left when I eliminate that row and that column. So that's 1, 2, 3, 1. Okay. Or 3 times minus 1 times minus 1 is plus 1. And here I'll have 1 minus 6. That's 3 times a minus 5 or minus 15 for the determinant. Let me show you a shortcut method that most of you probably remember from high school for a 3x3. It's a mnemonic device for finding the determinant of a 3x3 matrix. So let's look at this same example. 1, 2, 0, 6, 0, minus 1, 3, 1, 0. To find the determinant, I actually just take the original matrix, and then augment it by repeating the first two columns, 1, 6, 3, 2, 0, 1. And then I'm going to, starting here in the leftmost position, I'm going to add all of these diagonal terms going from the upper right, I'm sorry, the upper left down to the lower right. So the corresponding determinant here would be, on this first diagonal, I have 1 times 0 times 0, or 0, and then add to that the product of these diagonal elements, 2 times minus 1 times 3, so that's going to be a minus 6. And then this next diagonal is 0 times 6 times 1, so that's 0. So I add these terms. Then now I want to go along the bottom row, but now I'm going to subtract the diagonal, the product of the diagonal elements going from the lower left to the upper right. So I have minus 3 times 0 times 0, which is 0. This next one is minus a 1 times a minus 1 times a 1, so that's minus a minus 1. And then for this last one, it's a minus 0 times 6 times 2. And so here I'm going to get minus 6 minus a minus 1. So I get negative 5 for the corresponding determinant of this 3 by 3 matrix, and then that's the same result I had here. This is the minus 5 that appeared for this determinant. Okay, I'm going to end this first video here. It's gone on for a few minutes, so let you take a little break and return and talk a little bit more about determinants for today.